Welcome back to EECS 280, everybody. I'm guessing that every empty seat represents someone who feels totally screwed on their Euchre project. I'm glad you're here. So let's see. Project 3, due Friday, stay strong, use that debugger, you can do it. That's all I got to say about Project 3. We're going to keep going with dynamic memory today, and we're going to see some of the things that can go wrong with new and delete, and then I'm going to show you some of the solutions that we have in C++ to deal with the trickiness of dynamic memory. But this morning I woke up and I looked out my back window. My chicken coop is in the backyard, and I looked out there. It was still dark outside, and there was a possum trying to get at my chickens. So I kind of watched him for a while. I've had real problems with possums before, like dead chickens kind of problems. I know, but luckily that did not happen this morning. The coop was locked, and the possum eventually went to bed. So I'll keep you updated. But that's all I've got to report today. I'll be taking suggestions after lecture. Okay, let's review the important points from last time. We're going to build on several lectures we've used in the past today. So I need you to be with me on what we've done in the past. We learned about how to make a container abstract data type. And one of the examples I used for container abstract data types was an unordered set. We learned how to do templating with the unordered set. Today, I'm going to leave off the template part to make for less code on the slides. It had a constructor that said, hey, size is 0. And we could insert items. We could remove integers. We could find out if an integer was in the set. We could query and say, hey, how big are you, set? And we could print the contents of the set. This thing was fixed capacity because we didn't know how to make arrays that could change in size. That's going to change today. All right, so else capacity never changed, and we used it to make an array. The array lived inside the class as a member variable, had 100 boxes. Remember this? So we had box 0, box 1, box 2, up to box 99. And then if else size, if it was 0, then we'd say, well, only look at the stuff on the left. That's an empty set. If else size was 1 and we had an item, or maybe else size was 2, that'd be else size 2. Only look at the stuff on the left. Am I jogging your memory on how the unordered set worked inside? Can I answer any questions about the unordered set and how it worked inside? Remember how we did a sorted version? We're not going to do that today. We're going to stick with the unordered version, and I want to focus on this array and how to make it get bigger and smaller. The member functions are the member functions that were the simpler ones, not the more complicated ones that kept everything in order. So these are the member functions that were for the unordered version. So then we can use our set, and from the outside, we can do insert, 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 and then print, and there's no duplicates. This is all a review of how the unordered set worked inside and how we could use an abstract data type to give us extra features in a container, like no duplicates. All right, then we took a break from containers, and we talked about dynamic memory. So when we learned about dynamic memory on Monday, we learned about this new kind of variable. You already knew about global variables, which are defined outside functions. They come alive at the beginning of the program. They go away at the end of the program. You knew about local variables in the past. Those are inside a function. They come alive at the beginning of a function, and they go away automatically at the end of the function. Dynamic variables. They are created when you call new, and they go away when you call delete. You, as the programmer, get total control, even if it's in two different function scopes. when the dynamic variables are created and when they go away. Here's how you make a dynamic variable. New int. That's a typo. So this box is here. This box is here. When we create a dynamic variable, that means we get another object in our program. So this program, from this line of code right here, we get two objects. One is a local variable, and one is a dynamic variable. And we see that we have two boxes in our memory diagram, one for each object. More questions? Okay, we already knew before Monday that functions and stack frames go here on the stack, and it grows down. Which was kind of funny when we first learned about the stack. You're like, wait a second, why does it grow down? Then it made sense on Monday when we talked about dynamic variables. When you call new, you add them to the heap, and the heap grows up. So the stack and the heap grow towards each other. All right, that is the review of the last bunch of lectures. Abstract data types, containers, dynamic memory. So now we're going to start putting them together. Before I start putting them together, I'll give you one last chance before the train leaves the station.
So like the slide where it like showed like 7 and 5 and then below it like 7, I think it was because it was like repeating. Yeah, 7 and 4 and then 4. Why is it on a separate line, or is this just how the program is set up?
So the question was, why are there new lines here? This is just, it was an implementation detail of how I wrote the print function.
Okay.
Not a computer science concept.
Okay.
So the way we draw the whole like memory diagram,
This, like this or like this?
like that, does it actually look like that in memory?
The question was, does it actually look like this in memory? The answer is yes. And if you want to find out for yourself, Google objdump. Objdump is a Linux command whose input is a binary executable file, and it disassembles the binary executable file into these parts.
When you're adding frames to the stack, do you push everything downwards, or do you add them to the bottom of the stack?
The question was, when you add something to the stack, which part of the stack does it go on? You add more code here, like this, to an address that's smaller than the address the last function used. Because these are the big addresses up here, and these are the small addresses this way. So I need you to be thinking in your heads today what stuff goes on the stack and what goes on the heap and what it looks like in memory. Because we're going to just have like a new and delete fiesta today. Yes?
So I was wondering how the compiler works as far as what it compiles first, the heap, the stack, or...
The question was about what order the compiler does stuff in. I'm going to say let's talk about that later.
If you pop something from the stack, then you would be last in, first out, right?
If you pop something off the stack, is the word for that last in, first out? Yep, LIFO.
So if you add something, the stack it goes down, and then when you pop something, you pick up the smaller one, and then let it go.
So when you add something to the stack,
Yeah.
you have to take this thing off the stack, the one that's the bottommost item.
Okay.
What's the bottommost item? It's the function that most recently executed. So it's all about the functions. The stack is all about the functions and the local variables that are in those functions. Okay, so now let's talk about the size of dynamic variables. With dynamic arrays, we can choose the size at runtime. This is different than all the arrays we've used so far in this class. We can choose the size at runtime. Store a pointer to the first item in the array. Here's how you do it. This is great if you truly have absolutely no idea how big the array should be. Are you with me that if we ask the user how big the user wants the array to be, we can't possibly get the compiler to predict what the user will do. People are pretty unpredictable, aren't they? So now we have the size, and then we call new to get an array of that size. Then we can use that size variable, and we can use the brackets. This code here is just like the code you've seen in the past with arrays. No surprises here. This part is different. We delete. Notice how this is a pointer to the array. So let me show you what this looks like in memory. So let me start over. So on this line of code, we get a variable called size. And let's say the user says 3. Then on this line of code, we get a pointer. That's an object in memory. And when I call this, I get 3 boxes on the heap. So this is the heap, and this is the stack. And then array points to the first item in the array. Why did I point to the bottom box? Do you agree that the first item in the array has the smallest address? Do you agree that the smaller addresses are lower in the diagram? Got it?
Wait,
Why?
is that just how the heap works?
So the heap grows up. So I'm going back. I'm trying to be consistent with this diagram here, where address 0 and the addresses go up the page. I realize this doesn't make a whole lot of sense for, I guess, English speakers, where we go left to right, top to bottom. Wouldn't make any sense for Mandarin either, because that goes top to bottom, right? So basically, it doesn't make sense for humans, but computers love it.
English and Mandarin.
All right, questions?
What can possibly go wrong?
What could possibly go wrong? Before we get into the wrongness, let me bring this into the class, and then we'll have lots of things go wrong. I promise it'll be a total disaster today. One more, and then I'll keep going.
How does delete know the size of the array?
How does delete know the size of the array? Because the operating system promises to keep track of it. Can I ask the operating system how big it is? Sorry, dude, no. So just like the arrays we used in the past, it's our responsibility to keep track of the size separately.
Why would the operating system refuse to tell you?
Why would the operating system refuse to tell you? You'll have to take that up with the operating system. We can talk after class. All right, now we're going to modify our unordered set to use a dynamic array instead of a fixed size array. So before, we had an array like this. On this slide, how do I keep track of my array? What kind of variable do I use? A pointer. So that's what I'm going to change. This is a pointer to the dynamic array. Something that has not changed is else size. That's the how many items are currently in the set. Are you with me that the number of items currently in the set could be different than how big the maximum size of the array is? And are you with me that we just made the size flexible, the maximum size? So now we have to store that too. That's why I need to add this. So the occupancy and the capacity. Size and capacity. Size and capacity, two different things. Size is bigger than capacity. Sometimes, always, never. Never. Size is less than or equal to capacity. Sometimes, always, never. Always. Agreed. All right, so else will point to a dynamic array. Else capacity will tell us the size of the allocated array. And then we're going to have a default value to know how big to make it or at first. So we'll stick with the number from last time, 100. And if we need a default value, we'll make the size 100.
How is having else capacity any different than having like a really big array and then using a certain part of it?
How is this any different than just having a really big array and then using a small part of it? What if we don't want a really big array every time? Or what if that really bigger, all right, actually I got a better answer for you. How big should it be? Do you agree that we have to answer that question if we're going to use a really big array?
Yeah.
Because you have to type something into the compiler. So how big should it be? Like 1 million? Well, what if I want to store 1,000,001 items? Which is not that unreasonable. So we have no way to know. That's the answer to your question. We have no way to know. All right, now we need a constructor. Before, this is a bug, and this should be else capacity. No. 0. There we go. Let me write that down. So before we set else size to be 0, we're still going to set else size to be 0. But now we will store the capacity. And then here's the big difference. Notice that this is inside the curly braces. This is a constructor that's got some hard work to do. It needs to say, please give me an array on the heap. The constructor asks for an array on the heap. The constructor asks for an array on the heap. This is the biggest change so far in the whole lecture. Constructor asks for an array on the heap. So let's make another constructor. Let's make a constructor where the other programmer can tell us how big they want the array to be. Are you with me? That because we're using new, we could make the array as big as we want or as small as we want. So it makes sense that we could ask the other programmer and they could give us any number and then we can make an array however they want it. That's what we're about to do. So now we already did this constructor, the default. How big is the array for the default? 100. How big is the array for the custom constructor? Anything. So now the alternate constructor only has one difference. We say, how big should it be? Store it. And then instead of making a 100 size, we make it a configurable size. We're still using new. And we're still using a pointer.
How does capacity work? Like if it's like how is it like able to be flexible, like changing stuff?
How can the capacity change? That'll be the second half of the lecture. Right now, it's flexible because the user can tell us what they want. In the previous lecture, could the user tell us how big they wanted the array? No, it was 100, whether you like it or not. Yeah. At least now you can say whether you want a size 3 array or whether you want a size 3 million array. We'll get to making it bigger in the second half of the lecture.
Okay. So you're initializing else size with null pointer. Is there any reason you did that instead of just writing 0?
So I use else size to null pointer. That's a typo. Thank you. This is a query replace problem. I made the mistake when I was editing these slides. I need to do a bunch of null pointers, so I said query replace 0 with null PTR. Anybody made a query replace mistake in their text editor before? Oops. Let's use a little function overloading. So remember that function overloading is 2 functions with the same name but different prototypes? That's like this. So we can create an unordered set with no arguments. That's the default constructor. We could also make an unordered set with an input. That's where the alternate constructor runs. Reminder, when you create an unordered set, exactly one constructor runs. We get to pick which one. These are really similar, though. See these 2 constructors? This one has no inputs. This one has an input. The only difference is that capacity. So this is kind of like copy-pasted code. I'm using this as an opportunity to show you a second way, or to show you a new C++ concept, which is called the default argument. You do this in the function prototype, and you get, it's like two functions in one. So now we only need one implementation. Now we only need one implementation. So if there's no inputs, we just assume that the user meant use the default value.
Can you make a subset of your arguments have default?
Can you make a subset of your arguments have a default? Yes, you can mix default with non-default. The defaults have to be at the end, like the rightmost arguments. And this is a common idea. Other programming languages have this idea too, where you can give the function arguments, or you can not give the function arguments. If you don't give the function arguments, there's a default value. All right, I just did a lot of talking. Let's just see what it actually does. Please draw the stack and the heap. You'll probably need to look at the lecture slot, look back through the lecture slides to see the source code for what we coded so far today. All right, let's take a look. One line of code. And if you can draw this picture, that means you understand what happened in like the last 6 lectures. So let's walk through it slowly. All right, what function runs on this line of code? Constructor. So let's go look at the source code for the constructor. Here it is. We're going to initialize the value of else size, else capacity, and else. We'll get there. Where does the variable called is go? Stack or the heap? Goes on the stack. And what are the members for is? We got to go back and we got to look at the source code. Here are the members that go on the heap. Sorry, here are the members that go on the stack. Where does this member go? Globals. Why? Because there's only one. How do we know that? Because it's static. That's what static means. There's only one. That won't cause any confusion because it's also const. So the different instances of unordered set won't mix up which one is which. So are you with me? We need to make 3 member variables in this thing. So let's draw that. So now we have is, and inside is, we have size, capacity, and the else pointer. What's the initial size? It's 0. And what's the initial capacity in this example? 3. So 0, 3. Then we get some source code that runs. What do we do next? We call new. And what does new do? Get variable on the heap. So then we get 1, 2, 3. And then else points to the first item. All right, how many items are in the set right now? 0. How many items do we have space for in the future? 3. More questions? And yes, I got the right answer.
Can we call delete on is, or do we need to make a function inside unordered set?
The question was about how do we call delete and where? I'm getting there. Let's make a bigger mess before we answer your question. I'll give you a few minutes to think about this one. What happens in this code? I'll give you a hint. Think about what happens to the picture on the previous slide.
What if I want an array with more than 4?
Do you agree that we have some local variables involved with this program? And they go away automatically? And do we also have some dynamic variables involved in this program and they don't go away automatically? Did we call delete anywhere yet? No. So somehow we're going to have a problem with that. So let's draw a picture here. This is the same picture I had on the previous slide. So main runs, the function runs. So foo, this is the stack frame for foo. Then foo returns. And are you with me that when foo returns, oh, sorry, ooh. Hope that's okay. It was free. Can I have it? No. All right. We didn't call delete anywhere, so this thing is still hanging out on the heap. Memory leak. Memory leak, memory leak, memory leak. So what if we called foo in a loop like this? What would that do? Just leak a lot of memory. If you want to have a good time on a Friday night, try that. And then chug until it crashes. All right. Let's talk about destructors. I didn't just say that. So somehow we got to call delete. And the time we want to call delete is when that local variable, when this thing goes away, we want the array to go away too. So that's what we need to make happen. How do we do this with a destructor? This is a function, a member function with a funny name. That is literally the name of the function, including that tilde character. It's a destructor. Typical use with a container like this unordered set, the constructor calls new and the destructor calls delete. Constructor calls new, destructor calls delete. So we already did step 1, now we got to do step 2. First, we need to add a member function and document it. So destructor destroys this unordered set. Remember, no inputs. This looks a lot like a default constructor. Here's the difference. Now we will implement this function. So implementation. When you call delete with an array, you have to remember to use this syntax. So we added a little bit of code. It does some pretty complicated things automatically under the hood. You have to know that this happens. This seems magical if nobody taught you this. It's not magic, but it does happen under the covers, and it's not obvious at first. So when does this code run? When does this function run? Destructors run automatically when an object is destroyed. When is an object destroyed? End of scope for all objects? Say again? If it's a variable on the stack and the function goes away, yes. But are all variables on the stack? No. Some variables go on the stack, some variables are global variables, and some variables are dynamic variables. So before you can answer the question, when does the destructor run, you have to answer the question, is it local, global, or dynamic? So if it is a local variable, then the destructor runs when it goes out of scope. If it is a global, then the destructor runs after main. More questions?
Can you overload a destructor?
Can you overload a destructor? You mean like with polymorphism? We'll talk about destructors and polymorphism at the end of the lecture. It's fairly intuitive, and it's the generally speaking, destructors are fairly intuitive if you think of them as the exact opposite of constructors. The exact opposite. Why do we need them at the end of main if the program usually ends there? You could do many things in a destructor. Like what if you released a network resource? or you said, oh, I don't need to lock that file anymore. I'm done with it. Those are all other examples when a destructor would be useful.
Is this slide saying that we don't have to call them?
Is this slide saying that we don't have to call the destructor? That's exactly what I'm trying to say.
Okay,
Thank you.
We still have to write them.
But we still have to write them, yes. You have to write it, and you never have to call it.
Got it.
I've only seen a destructor called explicitly once, and I never wrote that code. It's deep, deep, deep in the bowels of the vector class. I've been there. A destructor gets called automatically when an object is destroyed. Agree. And its purpose is to destroy the object. Isn't it already destroyed? Case in point. If we used new, then the answer to your question is no, it didn't get totally destroyed. It got half destroyed. So we made a mess by using new here. We made a mess on the heap. We got to clean up our mess on the heap. We know how to use delete, but we don't know when to call delete. Now we do. We call delete in the destructor. Okay, let's just do this again. I'm gonna go through step by step, and we're gonna look at which function runs and when. And I'm gonna repeat the first exercise. So we're gonna run one line of code, but it's gonna take a minute. We got one local variable. It goes on the stack. Its name is is, and it's a class type, and it has several member variables. Those several member variables are size, capacity, and the else pointer. Then the constructor runs. It sets size to 0, it sets capacity to 3, and it calls new. When I call new, I get a new array on the heap, and else points to that new array. So this is everything I did on the previous slide. You with me so far? Okay, now we get to this line of code. Does it look like a function runs on this line of code? It doesn't look like it, but you got to know that a function runs on this line of code. Because is is a local variable, is goes away. And is goes away. And the destructor runs. Okay, so now we got to go back to the source code, and we got to see what the destructor does. So we read the source code for the destructor, and we see that the source code calls delete on the else pointer. Here's how we call delete on the else pointer. Boom, gone. Then the function returns, and this is popped off. How much memory did I just leak? 0. All right, so there was your play-by-play for the constructor and the destructor. Lots going on one line of code, or 2 lines of code now that we count the closed curly brace. More questions? So does the destructor run right before the variable goes out of scope? Yes. Because the destructor needs to look at the member variables, use those member variables to do a sane job of cleaning up the heap. Okay, let's do it again. What happens here? I'll let you do this one. I'll give you a hint. There are no tricks here. If you use the rules that you already know about constructors and destructors, and you use the rules you already know about new and delete, you can put them together without any special tricks. Go. When I use the keyword new, are you with me that I get a new object? Yes. All right, where does that new object go? On the heap. Okay, guess we're making an int set on the heap. Size, capacity, else. Size is 0, capacity is 3. Then what happens? Constructor runs and creates an array on the... Okay, no problem. Where's my local variables? There aren't any. How much memory did I leak? All of it.
Would you leak the, I mean like the else would get deleted at the end, right? But still leak the other variables?
All right, so now I have I'm going to rephrase your question, okay? Does a destructor run on this line of code? So are you with me that destructors run when a variable goes away? And local variables go away when they go out of scope. How many local variables are in this program? 0. So what variables go away on this line of code? None of them. So how do we fix that? We got to assign it to a pointer and remember the location. We got to remember where it should go. So now by adding this code right here, we can save a pointer to where that unordered set lives on the heap. And then we can call delete. And then delete will cause the unordered set to go away. And when the unordered set goes away, what runs? The destructor. So this delete causes the destructor to run, which calls, what does the destructor call? Delete. So the first delete kills off this thing, and the second delete calls off this thing.
The only thing we have in the structure is delete the else with the other variables still be like in the memory or no? Like on the heap.
So remember we have 2 deletes. The first delete here removes this part, and then the destructor causes this part to go away. So we have 2 deletes. Do we have to write a destructor for player.cpp in project 3? No. We added a dummy destructor just so you wouldn't get compiler errors. You call delete, and that's enough. So we are not worrying about destructors in project 3.
So how does it like delete the one above the int bracket 3 bracket? Like if it deletes the pointer to that.
So the question was, if it deletes the pointer, how does it delete the thing the pointer points to? The compiler actually runs these in reverse order. It like makes a to-do list of what to delete, and it gets it in the right order.
Okay, that makes sense.
How does it make that list? The destructor is a function, and it adds it to the stack. That's how it gets the order right. Run this thing in a debugger. It's a good time.
You mentioned the compiler applying the destructor. So if there's a dynamic variable, will the compiler catch or require a destructor in your class?
The question was, you correctly pointed out that we use dynamic variables in this program, and that caused us to need to use a destructor. If you use dynamic variables, will the compiler be so kind as to remind you to use a destructor? Nope. Unfortunately. C++ is like it assumes you know what you're doing. That's the best way to put it. It doesn't do stuff for you automatically. It doesn't initialize variables to values automatically. It doesn't run code automatically. It doesn't remind you. It just assumes you know what you're doing, even when what you're doing is kind of like weird and obscure. So a dynamic variable, the destructor runs when the dynamic variable is deleted. Okay, we've made it far in to take a break. Let's take a 5-minute break. Let me give you a hint for studying this lecture, which you'll need to do, especially for the final. The hint is copy paste the code that I have in the lecture and then run it in a debugger and step by step into each function. You can watch exactly when the constructors run, and then you can see what the values of the variables are, and then you can watch exactly when the destructors run. They're real functions, and the debugger will show you when they run and when they don't run. So debugger is great for Project 3 and also great for studying. Can you tell that I love debuggers? Is there anybody in this room who still never really used a debugger and gotten away with it? Okay, I got to make the projects harder. Do you guys use lots and lots of print statements? It's like see out, see out, see out. Or do you just I think I read a comic recently. It was like, what's programming? It's where you stare at the screen until blood comes out of your forehead. Yeah, I've done that. You're like, I can't possibly be wrong. I wrote it. All right, so what is the computer science concept behind what we just learned? The constructors and destructors. RAII, resource acquisition is initialization. I don't really like this name, but hey, this is the name of the computer science concept. The general idea is that the compiler is terrible at managing resources. Like if you create dynamic memory, the compiler can't clean it up for you. But the compiler is really good at managing local variables. So, you know how they get cleaned up when they go out of scope. So what we do is we wrap up dynamic resource management, aka new and delete, in a class. And then you use local variables of the class to create the variables and then destroy the variables on the heap. This is what constructors and destructors do. New and delete. And this is exactly what vector, the standard template library vector does. This is exactly what the standard template library string does. So now let's talk about the most fun part. How do we make it bigger? Modifying insert. So now the client, aka the other programmer, can tell us what size inset they want. We made some small ones, like size 3. So what we really want to do is make an unordered set that gets bigger automatically as needed. Are you with me that insert used to have a maximum size? We're going to take away that, and we're going to use new to just make it bigger whenever we need to. So the only thing we have to change is insert. Everything else in the class just assumes we have an array, and that's still true, so it still works. So are you with me on what we're about to try and do?
Could you repeat it?
What are we about to try and do? We're about to modify the insert function so that instead of crashing when the array runs out of space, we're going to make the array bigger. That's the big point. Thank you for asking. So instead of crashing when the array gets too big, instead of crashing when the array runs out of space, we're going to make it bigger.
Does this also apply to making it smaller?
Does this also apply to making it smaller? We could do that. We're not. In fact, the standard template library containers, like vector, they just say, if you want to make it smaller, I'm not going to do anything. And that's how it works. There is a member function called make it smaller, but that's a 281 thing. So here's the old version. We had a requires clause that said, hey, don't put anything in here to make it overflow. And then we had an assert statement to check the requires clause because we are careful, defensive programmers. Here's the new version. Instead of crashing, we're just going to call a grow function. We'll write this grow function. So if the size gets all the way up to the capacity, we have 0 spots left. Agreed? So let's make more spots and then carry on with what we were doing. Questions about insert function?
So
How do we know how much to make it grow? I have an answer for you with math. So stick with me. It's even better than statistics. Have you ever heard about the 3 kinds of lies? There's lies, damn lies, and statistics. So now we got to write a function called grow. And then later we'll use math to decide how much we should grow. So we're going to add a private member function. Enlarge the else array, preserving the current contents. In other words, don't throw away what's already in the array, just make another slot. All right, unfortunately, you can't make an array bigger in C or C++. So instead, what we're going to do is we're going to make a bigger array, copy the small one into the big one, throw away the small one, and then update our pointers. Make sense? So let's do it. Actually, no, you do it. You know how to do this. Please talk with a neighbor about what kinds of code you need to write for 1, 2, 3, and 4. Spend the next 1 to 2 minutes doing that. And then I will write the actual C++. Look, so step 1, allocate a bigger array. Else capacity plus 1. Bigger array, right? Spot for one more. Okay, cool. And then we will copy the contents from the old array to the new array. Then we will delete the old array. And then we'll copy the new array to the member variable. And then update the capacity. So for a while, we have 2 arrays going at the same time. One that's size 100 and one that's size 101. Or whatever the size might happen to be. I should be more specific. Capacity.
So how come else and else capacity are, how come those don't get deleted? Is that just...
How come we don't delete else capacity?
Or, like else or else capacity, because I thought if you delete like the old one, right, you delete the stuff that's with it, and you would have like new variables called else and else capacity.
How come we don't delete the old array? Is that the question?
Sort of. Like, does the old array have its own else and else capacity or no?
Does the old array have its own else and else capacity? Okay, how many unordered set objects are we dealing with in this whole function? We have exactly 1 unordered set object. So, you know what, let me just, let's do this. This is going to take a hot minute, okay? We got time. But I'm going to have to sit down. And then we're going to have to use some colors. So we will start with main, and we'll allocate an unordered set is, which goes here on the stack. And it has a size, it has a capacity, it has else, size 0, capacity 1, yes? And then we call new, and we get an array with 1 box, else points down here. Then we run this line of code, we throw a 1 in, size gets up here. Everybody with me? Did I go too fast? Ready for the next line of code? Here we go. So then the fun begins. So we're working on this line of code right here, and we want to insert a 2. So I call insert if index of blah, blah, blah. No, it's not in there. Okay, so now we go here. What's else size? What's else capacity? Should we grow? Yes. So now we go here. All right, now things get interesting. So we've got this is the stack frame for main. Now we have a stack frame for insert. And now we have a stack frame for grow. What are the local variables in the grow function? Temp and I. Good? Okay, so then we run this line of code, and we get a new array on the heap, like this, and temp points here. Still with me? Okay, so then we go to this line of code. I'm not going to go through this step by step by step by step. We're just going to do that. Good? Can I answer any questions about what I've done so far? All right, so then we go here. We see that else points to this array, and we call delete. So this thing is gone. Else still points to the wrong place. You with me? Else points to the wrong place. We need to fix that. Temp points to the right place. So we patch that up. I'm even going to use a different color on this line because it's so important. Ooh, what is a good color to make this? Purple. I love purple. Okay. So then else now points to the same place that temp points to. Then else capacity is truly bigger now. So now we can make the capacity 2. Then the grow function is done. So its stack frame gets popped off. Then we do this line of code right here. And this line of code causes, by the way, this is a 2 right here. So we get this 2, and then we make this bigger, and then we return. All right. Now we are on this line of code. Before this line of code runs, do we have the correct and now bigger array? Yes. Did the array get bigger, or did we get a brand new array? We got a brand new array. So what runs on this last line of code? Destructor. And what does the destructor do? It calls delete. And what does it call delete on? On else. And what does else point to? This array. So this is gone. And then this gets popped off the stack. And then main is over. And everything, and we have no leaks. Okay, that took me a while. Can I answer any questions about what just happened? What's the first if do? Oh yeah, what's this thing for right here? This makes sure there's no duplicates. That has to do with the duplicates.
So the reason that else was deleted from the heap, is that because the destructor manually removed it?
Sorry, I just thought of something. Say that again.
So why was else deleted from the heap? Because my initial thought...
Why was else deleted from the heap?
Well, I mean, I know why. How? Did the destructor do it?
So at the very end of the program, like right here, Why did we delete the array pointed to by else? Like, how did it get deleted? Because of the destructor. So the is variable was a local variable, and the local variable went out of scope. When the local variable went out of scope, its destructor ran. When its destructor ran, if you look carefully at the source code from earlier in the lecture, we saw that it called delete, and that's how we knew that it gets removed from the heap. All right. One more. How efficient is it to grow by one every time? I thought you would never ask. Notice on this line of code right here, we copy one array item. So with this program here, this is a main function, how many individual copies do we make? Now we're going to answer your question mathematically by measuring the copies. You're with me that the copies are, we're going to be doing lots of copies eventually. So let's count them. On this line of code, do we need to make any copies? No. On this line of code, do we need to grow? So how many copies do we need to make? 1, because the old size was 1. All right, on this line of code, what was do we need to call grow? Yes, so how many copies do we need to make? On this line of code, do we need to call grow? How many copies do we need to make? All right. How many elements are copied? Wrong. How many items are copied? Think. Think about patterns. You're on the right track. All right, now we're getting a little bit from 280 territory to another taste. The last 10 minutes of class are a taste of 281. You'll learn how to do this rigorously for any kind of code in 281. We're going to do it by example for today. We're just going to look for a pattern, and then we're going to apply a pattern. So I'm going to blow this for loop up by copy-paste. So do you agree that we start by inserting a 0? Over here, we do insert I. And then we're going to insert 1, and we already figured this part out. But then when we go to insert n-1, are you with me that that's the last time we need to do this? And that we're going to do n-1 copies? See that pattern? So how many copies are there? 1 plus 2 plus... So what is there an answer to this problem? Yes. This many. How did I figure that out? Wikipedia. No, actually, so having a cheat sheet full of common summations is going to be awesome in 281. You don't need it for 280. So there's only a handful of these that are super useful for problems like this. So you get a handle on like 3 to 6 different summations, sequences, and series, and you've got these problems down. So do you agree that this is going to be n squared plus something? So what we really say is that the cost to build the unordered set grows with n squared. So the cost is quadratic. So your earlier question was, don't you make a lot of copies? One answer is yes. Another answer is, we make approximately n squared copies, which is awful. How can we do better? Well, we're going to change not just one line of code, we're going to change one character in our code, or 2 characters in our code. So before we did +1, now we're going to gamble. Every time we make this thing bigger, we're going to go to Vegas and we're going to double down. We're going to bet that this set is going to not just get bigger now, but it's going to get bigger in the future. So we're going to say, all right, I'm willing to pay for twice as much space on the bet that I'm going to use it in the future. So how do we bet in C++? There's no bet function. All right. Instead of else capacity plus 1, we're going to do just double down. So times 2. This is the only difference from the previous code. Instead of 1 extra slot, we're going to get double the slots. Why double? X281. I'll give you an example that answers why double, though. When we do it this way, let's measure the copies now. So how many copies do you make? Are you with me that copies are what made this expensive? So let's count the copies and let's see if it's less expensive. So now I ask you the same question. How many array elements are copied? So I'm going to explode this for loop again, and I'm going to copy paste this line of code, and we're going to look for a pattern. By the way, this is how I solve in my head. I can solve lots of these X281 problems in my head, and I'm basically showing you what I do in my head when I solve those problems. I explode the loops into a bunch of lines just like in my brain and just look for a pattern. So let's explode the loop. 0, 1, 2, 3, blah, 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 blah. So here we get 1 copy and capacity is 2. Here's where it gets interesting. When I insert another one, my old capacity was 2. My new capacity is 4. So that means I get this one for free. Or rather, I paid for it up front. I paid for it last time. So then when I insert 4, I make 4 copies, but I double my capacity, and now it's 8. So now I'm good all the way up until insert of n over 4 minus 1. Okay, then I make n over 4 minus 1 copies until I get all the way to the end, n minus 1. Do you see how this pattern is a different pattern? There's still a pattern here, but it's a different pattern than the one we saw before. So here's how we solve this. An infinite number of mathematicians walk into a bar. The first one orders a beer. The second mathematician says to the bartender, I'll have half of what he's having. And then the next mathematician says, well, I'll have half of what he's having, et cetera, et cetera, et cetera. The bartender puts 2 beers on the counter and says, I'll let you guys work this out. And so that story tells us that the answer is 2n. And have you learned about recurrence relations yet in X203, for those of you who are in X203? Recurrence relations are related to how to take that story and turn it into algebra with a limit. That's why there are an infinite number of mathematicians. But that's not the point of X280. That's the point of X281 after you're done with X203. What I'm trying to give you is like just an intuition for why we did it this way. It's not random. Yeah?
Is there any reason you wouldn't just multiply by the bigger number, like 5, 10, or 100?
Why not 5 or 10 or 100? There's also a mathematical answer for that. And the answer is, well, 2n, 3n, what's the difference? They're all n. So we get a really big difference between something that's similar to n squared and something that is a lot like n, linear versus quadratic. Linear, quadratic. When you insert, this isn't that many. This is a modest number of elements. Copies there's a huge difference. This is how vector works under the hood. This is how many standard template library containers work under the hood. Double down.
Didn't insert take linear time before, though? Won't it already take quadratic time, even without the growing?
Didn't insert already take linear time before because we had to do a search? Good point. What's slower, searching or allocating memory and copying? I'll answer. Allocating memory is even slower, so you pay an even bigger price. Fair observation.
What if you just wrote a function? You could add an array, and when you pass in the length, it would just create a copy where the length increased by however many elements you were putting in. Then your time complexity would just be a constant, right? Or
The question was, what if you made a function that copied arrays into bigger arrays? Did I hear you right? So then we'd only have to call the function once. To analyze that code, we'd have to dig into the function you wrote and see how complicated that function was. And then we'd have to mathematically analyze that function and use that result to mathematically analyze the function that called it. And I argued that that function would have to use a loop. And we'd be in a different implementation of the same fundamental problem.
What if instead of copying the first bazillion elements, we just put a little pointer at the end to the next bazillion elements?
What if instead of copying the first one, we made a little pointer to the next bazillion? The standard template library authors thought of that, and then they called it a deck. It's an actual data structure that works in a different way than vector. That's another one that we will save for the future. All right. I'm out of time for destructors and polymorphisms, so I wish you well with finishing up Project 3, and have a great spring break.